This is a presentation on target-based localization as an initialization procedure for simultaneous localization and mapping. What you see here is a three-dimensional model of a scene. In particular, this is my coffee table with a few brochures and magazines placed on it. I'm going to cover the steps for creating this three-dimensional scene in the following presentation. So the first thing I'm going to do is show you some of the basic steps. What you see up here is the target that I used to initialize the SLAM system. This is a magazine, and this was taken with a different camera that the actual SLAM was run from. It doesn't actually matter. And these lines are showing the correspondence between the video that I ran the SLAM from and the initial target. So this target here, I marked out these corners and marked down as metadata how long these edges were in order to get an initial map in real world coordinates. And what you see over here is this marked magazine in a frame of the video data where we had found the correspondence and initialized the map from. So from that, we have here a representation of where the camera is in the reference frame of this magazine. This is a three-dimensional coordinate, which you'll see here afterwards in a live running mode. But again, this represents the camera, and this little block here represents the magazine that we detected. This here is the initialization of the map, and all these little circles here are the reprojected three-dimensional representation of this target onto the image of the target. So then, as we proceed through the SLAM session, you'll see more dots appear here, and that's the world being grown, the understanding of the three-dimensional representation of the world that the camera is moving through. And because we initialize with this target, the map is being built in real-world coordinates. In this case, I'm using meters with the origin, the corner of this magazine. So, and then you'll see, even as the target goes out of the scene, you can still localize the camera in the coordinate system of the magazine. Even this you'll see this here is the initial target, and the camera is not viewing the target in that scene, but it still is localizing it in the correct space. So this is the SLAM system running. I'm asking it to run at about half a second per frame, and this is the initial target, which I initialized the SLAM system from, and all these points are map points in the SLAM system. And as it continues to move away from where it initialized the system, every time it's about 10 centimeters away from any keyframe it's seen before, it attempts to grow the map. And as you see, it's gotten away from the initial target. It can no longer see that target, but it continues to be able to localize the camera based on the map regions that it's grown. And because we started with an initially known scale target, it is tracking in real-world coordinates, in this case again millimeters. And as the target comes back into the scene, it's drawn this red line around it to indicate that it has found the target again. And this could be used to further constrain the system or to relocalize if it in fact got lost. But in this case, it's tracking with a relatively low reprojection error, and so the system is continuing to track and map. So again, this is running at half second per frame. It runs considerably faster than that, which I'll show you here. So this is the system running at full frame rate. Right now it's all on one thread, which it could be made a good deal faster if we split up the key point finding and the SLAM processing. So it's going to run through this system, and afterwards we'll dump out a bunch of wavefront object files, which we can then display the world with. So we're going to be using MeshLab here to display the output of that SLAM system that we initialized from a target. Each of those keyframes produce a wavefront object file that shows the three-dimensional structure that we generated with that SLAM system. So again, this is that coffee table. I'm gonna and we initialized from this target and then grew this other three-dimensional structure. And what we can see here is that, well, that this thing should be about 20 centimeters across. We know that because we use it to initialize the system, and it looks to be about 20 centimeters across. But what's probably of more use to us is that we can make measurements in things that were not originally measured. So this is about, I know this to be about 10.2 centimeters across. It looks like 10.3 there. And we'll just make one more measurement. Between these corner points, I know to be 19.7 centimeters. And so, measure that, and 19.8. So indeed, this has set the scale of our SLAM system, and we can make measurements in real-world coordinates, based on what the SLAM system has reconstructed.